Welcome to another Unnecessary Computer Things. Today we are going to actually be timing some loops produced in BASIC and produced in C and assembler running on the Commodore 128. First I'm going to go through the C and up at, I will include this file in the project folder for this episode, but this will be compiled with cc65 using just the shortcut linker, uh, and then the C128 target, and then this file. So I did a few things with this file. I have actually some macros here. So I have one that actually combines all of the bytes, since the TI byte in Commodore land is 3 bytes. It's at 160, 161, and 162. This actually computes it assuming that Jiffy time is like 3 full bytes. And then Jiffy smalls, it's 2 bytes. And then Jiffy low byte is just counting the very lowest byte. So what we're looking for here is for the Jiffy timer to be 60, which means really we don't really need to count all 3 bytes or even both bytes. We just really need what's in the low byte because 60 is still within the range of that. I'm also including a Jiffy time function, and we'll see the weight of that function call. So you're actually doing this, and this is no inlining in here, so this will actually generate a jump. So first run is Jiffy time. Second run is the macro version. Second is just the 2 byte version, and the third is the 3 byte version. So if we go in and attach the smart image, and this is already compiled, and then run, and you'll see that first one, you're only getting, this is how many loops you're getting. So you're getting 1,110 loops, and then the macro version of that computes all 3 bytes, assuming that they're there, is a little bit faster, but not too much. So there is a little bit overhead with the jump, but also just the fact that you're calculating all 3. And I made this mistake early, but yes, I am resetting the Jiffy time each time, and I'm also resetting the I counter. So these are not cumulative; these are like individual runs. So the 2 byte version we have here. That's the third run right here. So this 8524 is how many runs you get by just lopping off that extra byte. And then, so that's one less addition and one less multiplication, I believe. And one one thing to think about, why is that such a huge jump from here? Because it's like just 2 more operations, right? No, not really. Um, if you're multiplying by 65 536, you're now no longer going to be able to fit into like a 2 byte word. You're going to have to actually use 3 or 4 bytes. So that's part of it, is just the amount of space. Those operations that's doing now are much slower in the assembler, in the assembly language, than the 2 byte operations. Once you get beyond 2 bytes, you start drastically slowing down. But you notice, so this is a 2 byte version. It stays within the 2 byte range, and then the single byte, where you're just looking at the low byte, which is all that really matters for this case. You notice that you have 9825. Okay, so that's not a huge leap. It is reducing two operations, reducing one multiplication, one addition, but it's like an 11% increase. So not huge there. And then we exit. So this was interesting. So jumping over to the C64 Studio version, one, this was interesting to get running. Had to learn a lot about like mapping these locations. These symbols, these labels can be mapped over to the basic file, and then you can refer to them. So if you add additional code up here or down here, and these bytes move, you can still have have the relative locations by symbolic locations. Um, and then since we're running in Commodore 128 Basic, you have to select V7. I think V2 for 64. One of the reason for that is these keywords actually get compiled to like 2-byte symbols, so that table is slightly different and it's longer for V7. Like some of these commands don't even exist. Actually, not but they're possibly a different location. So one thing I had was I was getting a on this peak, which is definitely a command that Basic 2.0 has. Uh, it was returning a type mismatch error because it was interpreting it in a different location and probably running a different basic function or basic statement. So, but as you can see, so for this, we have 3 tasks going. So we have the assembler loop, and we're loading zeros in here. We're initializing. Actually, I think this is redundant. The stores of A0, A1, and A2, which are, well, no, these aren't redundant because which A0, A1, and A2 are that 160, 161, and 162 for the timer. So we're loading up these index registers and the accumulator LDX, LDY, LDA with zeros. And then we're taking that 0 from A and shoving it in each of the 3 bytes for the system timer. So that's the TI variable when you multiply this one by 65,536, and this one by 256, and this one, and then add them together. These are probably redundant because I'm also initializing down here, and you notice that I'm not actually initializing high and mid byte. So I think I missed that there. But actually we can make that slight modification so that we see we don't want to accidentally have a higher count than we think we should have. Okay. And so here's a loop. We're actually starting through, we increment x if branch not equal is going to check the carry flag. So if we went from 255 to 0, then we need to increment y as well. So x is our low byte, y is our mid byte, and then we're going to use a memory location for our high byte if we need it. And so if we wrap around to 0, then B and E is going to not do this jump all the way down to here. It's going to continue on to this increment y. And then if you loop over again, then it's going to skip this again, this carry operation here. So if you need to carry after incrementing x, then it's going to fall through to increment y. If you need to carry after incrementing y, it's going to fall through to the high byte, and then increment the high byte at the location. These are implicit to the registers themselves. This one increments whatever you tell it to increment. So a memory location, it'll do the offset stuff, all that kind of stuff. All the different memory mapping operations that 6502 assembler does. So this is no carry. So if you don't have any carries in any of these, it jumps down to here and then immediately does a comparison to A2, and A2 again is our 60, or is our low byte. So we're looking for 60 there. And so how are we comparing it to 60? Well, it's up here, and actually that's not right, because what is hex 60? It's not that. So this result will be a little high. We need 60 to hexadecimal, which is 3C. So we actually want this to be 3C, not 60. So 3C is 60, so that's 48 plus C, which is 12. So 48 plus 12 is 60. So that's the value we want. And the value in the accumulator A is what's going to be used for the comparison. So if A2, location A2, is greater than this value 3C, so if once the timer gets above 60 or 3C, then it will no longer set the carry flag, I believe. And so this branch carry set loop will continue until we get, I think, past 60. So, or 260. So comp A2 will, for anything less than or anything less than 60 will clear the carry flag, and then this loop or will set the carry flag. And it's really hard to keep these straight. I'm planning on kind of linking out some resources on this, because this carry, these flag statuses are fairly complex, even though there are only like 4 or 5 of them. And they're, one of the things is they're poorly named. They're still the same conventions used today in modern processors. So these naming conventions have not gotten necessarily better. But since if you are still doing assembly now, you've been doing it for a while and you've just gotten used to it. So it would hurt more probably to change them, because you'd have people with muscle memory there. So if we get to 60 or greater, it's going to fall through this loop. It's no longer going to do this branch of carry set back to this loop, and it's going to drop to the low byte to store the low byte, which is, so we're using X. We were using X and incrementing X along the way for the low byte, and then using Y and incrementing Y for that middle byte. And then if we fell through all the way, we incremented the high byte. And since the high byte's already set, we don't care to set it again. It's already the value we want. So the only two we need are to set the low and mid bytes. And then we return. So this RTS is returned back to the caller. And that's where we hook in from here. So this loopy basic file one thing it's going to do when you're doing loads, uh, load 8 ones will not reset your variables that you've used, so you can actually check this to whether or not you actually want to reload. So if you've already loaded like A0, then A equals 1, okay, well, just go ahead. If A equals 0, then load this program. If it's not, because you've said this is like a second run or something, it's already in memory. Here's that sys start, which going back to here refers to this label. So we'll start at the very beginning of this program and run until it hits the return or a break or something like that. And so from there, we're referring to those high byte, mid byte, low byte via C64 Studio's linkage to those labels here. And so high byte times 65, 65536, and then mid byte, and then low byte. You could also just keep multiplying by 256 every time you do another addition. That works too. And so you see we doing the TI string set to 0 for the rest of these, but not for the assembly loop, because that's the second thing we do is these store a value of 0 into A0, A1, A2. The reason I'm doing that is because I don't want to count the overhead in calling over, so as time spent getting here. I want to have as much of the time for the loop itself to see how many loops can happen within that 60 jiffies, not count all these other operations, or more importantly, this jump by the syscall. And actually, not just the jump, but the interpretation of that sys will also take some time that I don't want to be burned for running the loop. And then down here, I'm doing also a for loop, saying, okay, break if greater, or like exit out, go to out of the loop. There's no break in Commodore Basic 7. So we're doing a then 80 to break out of the loop though, and then we print the value of I that it's gotten up to. And we're using one base here, which may be a little, let's see. Okay, so these other counts are low by 1, which really doesn't matter. But so I'm actually resetting to 0 instead of 1. But so we start with the counter with 1 each time here. In this case, where it's actually implicit to the for loop, so there's I1 to, let's say, 20,000. I know it won't get there, but because the C version didn't. But we're going to arbitrarily high. So this for loop, and then once we break out of the for loop, we'll print what value I got to. And then we'll do a kind of like a loop forever type of loop here, an infinite loop. But then what we'll do is we'll set the counter to 0, or timer to 0, counter to 1. And then if we've already gotten past 60 or equal or past 60, then we'll break out of the loop with a go to 30 to print this value. Otherwise, we're going to increment and then loop back and do the comparison again. So these two lines are our loop. And let's compile and run it and see how long it goes. So that's interesting. So when I was first running this, I didn't include the high byte, and so I was getting incredibly low numbers, because if you print 6036, it's not tiny, but it's a lot smaller than you would think it would be. Um, so and actually, so also what I was getting was I with that 9C. Actually, well, let's change this to 60. Okay, and run it. And what you'll see is this is 132. Okay, so you okay, so if you subtract that, it's 930. So what was happening was when I had this coded wrong, so I had it as 60 instead of 3C. So it was wrapping around that mid byte twice, or that high byte twice. And so it was actually coming up with this result, but I wasn't storing the high byte or reporting on it. So ultimately, it looked like I was only getting 930 loops out of this, which is smaller than the smallest result for the C program. But exit out. Let's restart this with the right numbers. And now you can see. So let's look at this compared. So at its worst, and this I think is fairly optimal assembly because I took care to use the index registers. You can actually, if you use the high byte directly, you can have a different result. Um, Actually, we can experiment with that. But so this is like almost 10 times as fast. But then you look at the for loop. For loop is about an eighth the speed of the slowest C operation. And then the goto, obviously the goto is not that efficient. And part of the reason is so with for loop, some of the loop handling itself is going back to machine language. Even though you're writing in BASIC, you have this interpreted down below, and that makes it a little more efficient, uh, twice as efficient almost. Versus this, you're actually evaluating the comparison operation and doing the comparison basically in BASIC, and then you're doing the increment in BASIC, which is, I mean, there is a native increment operation here, so uh, we can actually see. So what if we didn't optimize for the location? We said okay, increment low byte, increment high byte, mid byte, and then we have to comment these out, and we don't care to store because we don't care. So this is 82 439 right now, and we can see if this will actually build. So those, if I recall, so that's about 30% slower. If I'm recalling correctly how these operations map out, the increment X is basically, I think it's a two machine cycle operation, and so is increment Y. And also, it's like you're not, it's a single, I believe it's a single byte opcode that's involved. Well, you can see when you swap them out. And we you save it and watch it update. So yep, okay. So C17 for increment X, and then we commented this out so we don't, that doesn't compile anymore. Branch not equal, no carry. That's 2 bytes plus 2 bytes. So, oh, actually, I'm off there. So there's the number of bytes there. There's the number of bytes there. So that's a 1 versus a 2. And if you, I'm not going to run it again, but if you look back at this one, this is 3 bytes. So it requires 2 more bytes to just describe what it's doing. Um, the reason why that is, you can actually you could select some space in that in what they call zero page. These values are zero page. They're like the first it the implied value is 00A0. So if you can grab storage space uh, in the first 255 bytes of memory, then your operation is a byte shorter. That's popular memory for system purposes too. So there's not much wiggle room for that. So you kind of have to resort to absolute addressing or index or something to that effect. But then uh, so you have to since it's absolute, you actually have to specify both bytes here, and then you still have to have the operation that you want to do on it. So that is automatically 3 bytes. Where the performance comes in for this, also though, is that that addressing takes some clock cycle, like an extra clock cycle as well. So you end up, I believe, with for this increment operation, it's actually 3 clock cycles versus 2 clock cycles. It's definitely increased, and you can see it in the difference between the 82,000 loops that you got through with the more optimized version versus the 60,000. But you can see also that this index, using the index registers, and I'm using A, X, and Y, and those are basically what you get with 6502 assembly. That gets you 10 times as fast as a C compiler that it's probably not super optimized. But the C is writing ultimately assembly as well, or machine code as well. So at this level, like this level of effort with the C program versus or C compiler versus the amount of complexity behind the assembly language, you can actually optimize assembly yourself better than a C compiler can. Now it's not that's cc65 isn't the like professional or enterprise grade compiler that's big on making sure to do all the optimizations possible. And it is still, regardless of how inefficient you make your C code, it's still faster than even the basic for loop that is mostly jumping to machine code to run. So I just think that's pretty interesting. One of the applications I'm going to do with this, and I think I'm going to be doing it in C, is using this as a timing loop for building out a multi-track player. So but this was an interesting excursion into seeing how fast each method was, and I really wanted to save it until I could actually get the assembly loop working, which required me to get C64 Studio running as well. I'll have a blog post on getting that up and running. One thing I will say is, so make sure that your basic is targeting the right platform that you're building for. Uh, Go in when you're doing properties. Uh, you want your basic compile target to go to D64, and there's a sample project that also tells you this. Within There's a combining basic and assembly sample project in C64 Studio that does this, but I had to play with it just a little bit. But you select your D64 target type here, and then when you include your assembly as, oh nice, it's not actually pointing to that, I believe. Oh, maybe it is. Okay, I did open up the wrong one. Oh no, okay, never mind. I didn't rename the project, so it is this. Like, am I showing? Okay. So when you include your assembly file here, make sure it's dependent with an A and symbols. So the if you don't click those, you will get compile errors on the basic file. So let's see. And then curly braces on these. And then definitely another piece of this is making sure you have your Vice emulator or whatever emulator set up in C64 Studio. So you'll actually, there you go. So you got available tools. Need to make sure to add that entry in there. Anyway, that's all I had for today. Thanks for watching.